In this video, we're going to talk about spanning trees. So, a tree is a connected graph with no cycles. A spanning tree of a connected undirected graph is a subgraph that spans and containing all nodes and enough edges to connect them all with no cycles. There can't be more than one minimum spanning tree for a graph, and the commonly used one in problem solving is called the minimum spanning tree. So, let's look at the completed graph. Right, here's one, and all of its various spanning trees. There's dozens, but they all connect all the nodes with the minimum with one per node. Okay, so what do we want to do? Suppose you want to supply a set of houses with electric power, water, sewage, or telephone lines. To keep costs down, you can connect the houses with a spanning tree. However, the houses are not all equal distances apart. All right, so here, this spanning tree has a weight of 79, here it has 82. To reduce costs even further, you could connect the houses with a minimum spanning tree. And a minimum spanning tree is a spanning tree that has the lowest weight. So here's a completed graph, and here is the minimum spanning tree. It's the spanning tree with the lowest weight. There are two major ways to find minimum spanning trees, Prim's algorithm and Kruskal's algorithm, and we'll briefly go through them. Prim's algorithm is as follows. This starts with one node. It then, one by one, adds a node that is unconnected to the new graph. Each time it selects the node whose connected edge has the smallest weight out of the available nodes connecting edges. So what's the algorithm? We're going to mark a vertex V as visited and include it in the minimum spanning tree. While there are unvisited vertices, find the least cost edge V to U from a visited vertex V to some unvisited vertex U. Mark U as visited, add the vertex U and the edge V to U to the minimum spanning tree. So here's some pseudocode. Create a priority queue to hold pairs of cost nodes. We're going to push 0, S into the priority queue while the cost of reaching the node S from the source node S is 0. While Q is not empty, we're going to grab the first item and pop it. Cost C equals the cost. Vertex is the second one in our pair. If the node V is not present in the spanning tree, add node V to the spanning tree. The cost of the spanning tree is add the cost of C to it. For all the vertices adjacent to V that are not in the tree, push them into the queue. So let's look at an example. Here's a completed graph. So our new graph is as follows, and we're going to follow the algorithm and find the minimums, right? Here we go, and we're going to make sure that we encompass all the various nodes by when we look at a new one, we remove the old ones. Similarly, here we find these, but when we find a shorter path, we drop it out, and so forth. There's our minimum spanning tree. Okay, and now we're going to run through and make sure we have the minimum span, removing the nodes we don't need, until finally we have our minimum spanning tree. Kruskal's algorithm is a little different. It creates a forest of trees. Initially, the forest consists of n single node trees and no edges. At each step, we add one edge, the cheapest one, so that it joins the two trees together. If it were to form a cycle, it would simply link two nodes that were not already part of a single connected tree, so that this edge wouldn't be needed. So the forest is constructed with each node in a separate tree. The edges are placed in a queue until we've added n-1 edges. We're going to extract the cheapest edge from the queue. If it forms a cycle, reject it. Otherwise, add it to the forest. Adding it to the forest will join two together. Every step will join two trees in the forest together, so at the end there will only be one tree. Efficient testing for a cycle requires a union find algorithm, which we're not going to go over in this class. But here's a completed graph, and here's all our subgraphs, right? We're going to find a priority queue, but not sorting. But by sorting, it makes it easier to visualize, right? So we're going to first join our two trees, right? Then we're going to pick the next and match them, and so forth. And then here's our completed graph, which we've broken down. So does the minimum spanning tree give the shortest distance between any two specifies? No. It asserts that the total weight of the tree is minimum, but it doesn't mean the distance between two nodes is the minimum. Also, the shortest path tree is not guaranteed to be a minimum search tree. Another important difference in the type of graphs work on is Prim's work on undirected graph, while Dijkstra's works on directed graphs. So, Kruskal is a better running time if the number of edges is low, while Prim is better for a larger number of edges. So, it depends on your data and your structures.